This example is on static equilibrium on page 27 of your class notes, and it's example 18. So, static equilibrium the definition is the object is at rest and the resultant force is zero. So resultant force, remember, is addition of vectors. And if it is a zero vector, that means that it is going to be 0, 0. So here's the problem. A box of supplies that weighs 1,000 pounds is suspended by 2 cables attached to the ceiling. What is the tension in the 2 cables? So I'm going to first of all label this. So this right cable right here, I'm going to put an upward arrow this way and label this as R, representing my right cable. So R is equal to the right cable. And then the left one here is L, and that is the left cable. And then you have the box, which is giving it a downward force. So this right here is creating a downward force, or the vector that's going downward, and I'll call that as my D. So D is equal to the downward force. And that's basically the weight of the box. Okay, so when you're doing vector addition, I'm going to be taking the right cable, the left cable, and the downward force. And so if it is in static equilibrium, that means that it has to equal 0. Right? So that means that the right cable plus the left cable plus the downward force has to equal 0. And in other words, it has to be x component is 0 and the y component is 0. Okay, so I'm going to transfer these vectors and I'm going to draw it and move it around. Okay, so let me draw another coordinate axis. Okay, so the vector that I have right here, which is the R, I'm going to place this right here, as my origin. So I'll place it right down here. Okay, so here is my R. And then I'm going to place the L with the terminal point here, and then the L is going to go up towards this way. Right, so as long as I have the same magnitude and the same direction, it's equivalent. So this L can now be transferred down to here. And then the downward force is going to go from here, the terminal point of L, down to the initial point of R, and it's going to end up at 0, 0. And I'm forcing that to be that way because this is static equilibrium. Right, so this is going to be right here, and this is my downward force. Okay, so what I've done here is just to create a triangle, and now I'm going to put in the angles. Alright, so I'm going to create a right triangle by drawing this, and it's going to be parallel to my x-axis. Right, so it's going to be right up here, and it's going to be parallel. So I'll just make it a dotted line for now. And then this is going to be a right angle, and this is going to be a right angle. Alright, so what I'm going to do is now transfer some angles. So if you look at this 35 degrees, that is equivalent to this 35 degrees here. Right, so this right here is 35 degrees. And then if you look at this one here, the angle up here so if you look it up here, this is going to be the same angle, 40 degrees, as a 40 degrees if I were to draw it out right here, right? These are called alternate interior angles in geometry. So this 45 degrees here, and then the 40 degrees here and 40 degrees here are equivalent. So this is going to be 40 degrees here. Okay, now I'm going to look at the top right triangle. So if I have a 90 degrees here, 40 degrees, so then this has to be 50. And then down here below, I have 35 degrees, 90 degrees, so this has to be a 55 degrees. All right, so I'm just basically making this oblique triangle into two right triangles. Now I'm going to add up the angles on this side. So this right here, these two angles added together gives me 75 degrees. Okay, so now if you remember from our previous lessons, we talked about an oblique triangle where you have this side right here, the length of it is going to be the weight of the box, so this is going to be 1,000. Okay, so now what I want to find is, and I'll just put this as the magnitude here. Okay, so all of these are magnitudes that I'm trying to calculate, which is the tension. So this, and this one here. Okay, so then I have 75 degrees, and then the side opposite that is 100. So I'm going to apply the law of sines. Apply the law of sines. And if you recall that, basically it states that if you have a sine of a certain angle, and then the side opposite that is equal to the sine of another angle divided by the side opposite that. Alright, so for our purpose, we're going to be using the side opposite is 1,000, and so the angle that goes with it is 75 degrees. So then that's going to give me sine of 75 degrees divided by 1,000, and that is equal to, so I'll solve for my right tension first. So then I'll have 50 degrees, and then it's going to be the side opposite that is the right tension. So it's sine of 50 degrees, divide that by r, and then just do my cross multiply, so, and then divide, and so then you end up with r sine of 75 degrees is equal to 1,000 sine of 50 degrees. So then the right tension is going to be 1,000 sine of 50 degrees divided by sine of 75 degrees. And punch that into the calculator, and you end up with an answer of r equaling 793.068 pounds. Okay, so that would be your right tension. This is the right tension. Okay, and then for the left tension, you'll do it in a very similar fashion. So I have sine of 75 degrees, divide that by 1,000, and that is equal to, now I'm going to be using this angle since that is the angle that's opposite the left tension. So that will be sine of 55 degrees, divide that by L. Okay, and cross multiply again, so L sine of 75 degrees is equal to 1,000 sine of 55 degrees. Solving for L, L is equal to 1,000 sine of 55 degrees. Divide that by sine of 75 degrees. So my left tension comes out to be 848.049 pounds. So that is equal to the left tension. And that's how you solve static equilibrium problems.